All right, so now we will, as I was saying at the beginning, move uh, more in the direction toward learning, and we're basically going to add probabilities. And Benjamin's already set us up, discussing a little bit about that. But we're going to have two experts. So first, Fabio Cozman is a professor at the University of São Paulo in Brazil. Among other things, he developed creedal networks, an important kind of probabilistic representation, and is a former general chair of UAI. Fabrizio Riguzzi is professor at the University of Ferrara in Italy. Among other things, he co-developed PETA, an important probabilistic semantics, and is the author of a very thorough textbook on probabilistic logic programming. So these are two of the people who really helped develop um, the area as you see it. So let me hand it over to you guys.
Okay, well, thanks, Alex, for the introduction. I will try to share my window here. I hope that works. So, is that okay?
Yep.
Okay, so I will talk a little bit about probabilistic logic programming with a bit of neural stuff in it. So it's sort of a big mix. And this is work with my colleague Denis Mauá and Renato G, who's now was a programmer here and now heading to UCLA for a PhD there. So basically, let me just say a few words to introduce the mindset. We're looking at combinations of neural learning and representation and knowledge representation. This is a theme that has been discussed, for example, and has been classified in many ways. So if you look back in 2020, there was a AAAI invited talk by Henry Kotz on neurosymbolic AI, and he gave one possible classification of the methods, and there are many other ways to look at the neurosymbolic AI zoo, but you might have end-to-end systems that can do symbolic reasoning. They could solve satisfiability problems, for example. You could have neural engines that have an architecture that is based on symbols. So, for example, logical neural networks would be perfect fit for this, and this is a language, formulas that was developed at IBM by Ryan Riggio and colleagues. So you have a neural network that is specified using logic features, but you also have a number of other ways to have neurosymbolic systems where you have a module where this module may be a symbolic module or a neural module, and it calls one module, calls the other, maybe calls several times, maybe there's a pipeline. There are many ways to classify, but basically you have modules. You have parts where you have some parts are neural, some parts are symbolic. Okay, so I think one way to start looking at this combination of probabilistic logic programming and neural elements that we'll be talking about here is to think about neurosymbolic systems where the symbolic engine is calling neural elements, neural networks, is calling neural predicates, so to speak, to get some information about the world, maybe process sensing data. So you in some way you have a symbolic module that is being specified, and then it's calling the neural elements. And the symbolic, you could think about many different formalisms. The previous talk was, was a super good tour about the many ways to do the symbolic reasoning. There's one way that has been tried, and is to represent facts and rules using logic programming, which is something that Benjamin explained very well already. But then you have all these facts and rules about the world, and maybe at some points, they're calling the neural networks to do some specific work. That's the mindset. But then, in reality, you also need to deal with uncertainty That's something that has been around for quite some time in AI. And also because you're doing learning all the time, because you're dealing with neural networks that process data and they're learning, usually you don't have a 0-1 decision. Usually you have an answer that is produced by a softmax, and that can be interpreted as a probability distribution over the possible outputs of the neural network. So actually it makes sense to consider the symbolic module as a combination of facts, rules, and probabilities, which they are representing the uncertainty, and they are connected in some way to the neural elements. Okay, so I'll be discussing the left part of this picture for some time, and then later I will try to connect the circles here. Okay. So the combination of probabilistic logic and probabilities has been around for quite some time. There's been work on this from, I mean, for 30 years at least, maybe 40 years, I should say. For example, if you look back in 92, you had this formalism where you have basically a rule, as Benjamin explained, where if you have a connection between X and Z and a path between Z and Y with a probability that lies between 0.7 and 1, then you have a path between X and Y with probability in the interval between 0.85 and 1. Okay, so the idea here was let's have probabilities inside the rules. Okay, this was a bit complicated. So in around 95, a new idea was basically put together and consolidated by a number of people. In particular, Sato proposed what is called now the distribution semantics, but this was somehow proposed by other people before. The idea is actually quite simple and easy to understand, and I think that's why it's being picked up by many people since then. It's not very hard to understand what's going on. So basically, you have facts that are associated with probabilities. Like for example, here you have the probability of A is 0.2 and the probability of B is 0.3, and then you have rules. And the idea is that these probability facts are independent. Okay, they are assumed to be independent. So for example, if you want to know the probability of C, well, it's A and B, so it's 0.2 times 0.3, because A and B are independent. So that's the idea behind the distribution semantics. And with this simple idea, you can build very complicated probabilistic models. In fact, you can build any Bayesian network over binary variables. This is something that I think Fabrizio will discuss at some detail. But here's an example where you have a relatively short program where in yellow you have probabilistic facts, in red you have rules, and these rules can be drawn in this graph in your right. And then you have a few other probabilistic facts in green. They are just auxiliary facts, just to specify the probability that some rules will fire. The idea is, for example, you have a probability 0.01 that will be a trip. Trip will be true. And if trip is true and A1 is true, then tuberculosis will be true. Okay. So basically, you're specifying the story behind a Bayesian network with these rules. Okay, and you can see that this program is acyclic. Each atom depends on previous atoms, and there are no cycles. That's why the graph that you see in your right is an acyclic graph. Okay, so you have edges between the bodies of the rules to the heads of the rules, and this builds an acyclic graph. You can also have cycles in these programs. For example, here is a program that defines how you calculate a path in a graph. So you can have an edge, you can have a path. If you have an edge, you have a path, but you can have a path that is formed by several edges. So this is specifying, you can see that the predicate path appears in both sides of the third rule. Okay, so that's why there's a cycle. Okay, but it's a nice cycle because there's there's no negation in this program, okay? When you have a program that has no cycles with negation, we say it's a stratified program, okay? For example, you can use this program and you can specify a number of probabilities over edges, and basically you're specifying a random graph. Okay, so for example, you have a probability 0.6 that there's an edge between 1 and 2, and a probability 0.1 that there's an edge between 1 and 3, and so on and so forth. Okay? And then you can ask questions. You can ask, well, is there a path between 1 and 4? What is the probability that there's a path between 1 and 4? That's the purpose of these probabilistic logic programs. And then you can have also cycles. You can have cycles that have negation. When you have cycles that have negation, then things get more complicated. For example, here you have a person. If X is a person, then you have that if she's not a lawyer, then it's an engineer. If they are not an engineer, it's a lawyer. So it's kind of a cycle. You have two solutions basically. If the person if X is a person, they can be either a lawyer and not an engineer, or an engineer and not a lawyer. Okay, so you have two models, two stable models. That's what we say about this program. So basically, you can understand this program as follows. With probability 0.1, Dilbert is not a person. And then everything is false, because Dilbert is not a person, no rule will do anything. With probability 0.9, Dilbert is a person. It's true that Dilbert is a person. And then you have two models. One where Dilbert is an engineer, one where Dilbert is a lawyer. Okay, so you can, it's a bit difficult to say how we would distribute the probabilities, this 0.9 probability over these models. And there are several solutions. One, so when Dilbert is false, everything is false. But when Dilbert is a person, okay, when Dilbert is a person, then there are two stable models. There are two ways of understanding the program, and you could have different semantics. You could distribute the probabilities evenly between these two models. You could say, oh, probability 0.45, Dilbert is a lawyer, 0.45 is an engineer. Or you could take every distribution that distributes probability over these two models in any way. And in that sense, you get a set of distributions. Okay, so you understand this program as specifying a set of distributions in every possible way between these two models. One where Dilbert is an engineer, where one Dilbert is a lawyer. And there are also semantics where you will just say that the occupation is unspecified. There's no way to decide. And I think Benjamin also talked about the undefined value. This is what happens in those semantics. So you cannot decide. You can say whether Dilbert is a lawyer or is an engineer. Okay. Oops. All right. So you have several semantics. Okay. You have a semantics that's called a Maxent semantics, where you distribute probabilities uniformly when you have more than one model. You have the credo semantics, which means when you have several models, you consider all possible ways to distribute probabilities over them. And then you get a set of distributions, what we call a credo set. Or you may have a situation where when you're undecided, you leave things undefined. Okay? So there are several semantics. And there are several extensions of these languages, which I will refrain from getting into, because time constraints, I think it's better not to overdo here. But you can also have things like disjunction. If anyone in the audience knows about answer set programming, you know that you can have a disjunction like this. So you can understand this as if X is a node and X is not barred from consideration, then X is either red or green or blue. Okay, so it's disjunction that way. And you can have other things. You can have what we call strong negation. You can have something called aggregates, where basically you're counting, in this example, you're counting how many X's are birds. Okay, and this aggregate will evaluate the number of things that are birds. Okay, so there are extensions, and there's been quite a few results on the complexity of the languages you get. Okay, I will not get into this because this will take long, but just to give you a feeling of the results. So these are some complexity results for different languages, for different combinations of features, for when the program is propositional, when it's not propositional. There are several results, completeness results for complexity classes. And also this has been extended in many ways. So this here is probably the largest table on the complexity of this language that is available now. I wanted to say this has been studied as a serious knowledge representation language, and there's been quite a bit of understanding of what you can do with these languages. Okay, and basically with the logical part, you can specify a bunch of constraints, and then you can ask whether there's a solution. That's what you can do with the logical part, okay, with the rules and the facts. And you can decide whether, well, is there a solution that satisfies, is there a model that satisfies all these constraints and some other property? Or you can ask, well, for all models that satisfy these constraints, do they satisfy these other properties? These are things you can do with the logical part. When you have the probabilities, you can ask more things. You can ask the probability that there's a solution. You can ask probability bounds for a solution. Sometimes you cannot have a single number. You can compute the probability that the solutions have a property, a specific property. So there are more things you can do when you have these probabilities around. Okay, and there are a few systems out there that do these things, that calculate these probabilities. There's Problog, and this by Luc Derhaed's group, and he will be talking soon, so I will not talk much about this. Problog is very nice system, very solid system. There's been quite a few systems by Fabricio's group, Pita, CP Lint, and Pasta. I think Fabrizio will talk about Pasta in some detail soon. So I will also not discuss much about Pasta. There are a few other systems, like there's PASOX by a group by Dave Tukey at Imperial College and Alessandro Russo. And recently we have been doing, we've been coding here another system called DPASP, which is probably more interesting when you consider the neural part. So I will explain DPASP in a moment when we get to learning. Okay, but in short, there are systems that allow you to calculate these probabilities. Okay, now when you want to consider learning, you might consider, well, let's say I want to get the probability that this image has a particular digit. But this is actually calculated by a neural network. Okay, so I have a module that is thinking about the world and running rules and facts, but maybe this module will want to get some information from a neural network. So he wants to call the neural elements, okay? And there are several systems that allow you to do that. Deep Problog is the deep learning version of Problog. I think Luke will talk about this. This is a very nice system. There's also NeurAsp. NeurAsp is also an interesting system. It uses these max entropy, the maxent semantics for even cyclic programs, which is something that Problog does not do in general. So Problog is more constrained to stratified programs. But NeurAsp does for all programs. However, the problem with NeurAsp is it's a bit slow and it's not being maintained for a while. So actually, we decided to code a number of semantics and try to do this in a more friendly way, so that you can better interface with neural networks and the packages that we now have for deep learning. So we started coding this system called DPASP, and this is the brainchild of Denis Mauá, my colleague, and it's been mostly coded by Renato G, which is the other author here, I think. Let me say a few things. Oops. Sorry. let me say a few things about DPASP. The idea of DPASP is that it's looking at differentiable probabilistic answer set programming. So it has things like statements that assign probabilities to atoms. It allows you to do inference with many different semantics, all the semantics that I mentioned before. It doesn't have algorithms that are as nice as dproblog, but it's coded in C. So the idea is that instead of doing a lot of computation to compile these programs into very nice structures, it tries to do things, simple things, very fast. Okay, and I'll show you some numbers that will indicate that. Okay, and also you can ask DPASP to learn a probability by writing a question mark. Okay, so this question mark here tells DPASP that it has to learn the probability of burglary. If you write a number and the question mark, then it will start the gradient descent process of learning this probability, and all of this is done using maximum likelihood of gradient descent. So it will start the gradient descent process from point 3, and we'll look for the best probability for burglary in this example. One idea behind DPASP is that it tries to be as nice as possible to the programmers, so that the interface between the DPASP code and Python code is actually very simple. Okay, I would say simpler than the alternatives, but let me give you an example of what happens in practice. Suppose you have a neural network that is a Python function, it's calling a neural network that processes an image and returns using a softmax a distribution over digits. Okay, so you would write this in DPASP as follows: if X is an image, which is in the right side, then you should get the probability of X containing a digit between 0 and 9, 0, 1, 2, 3, 4, 5, until 9, using the neural net that is called by the function neural net. Okay, so this is telling DPASP that digit is a neural predicate, and the distribution of probabilities over the values of digit are coming from a neural network. Okay, all right, so that's the idea behind DPASP. Let me give you an example just to finish. I have maybe 2 minutes. This is a famous example in the world of neural probabilistic logic programming. It's you get 2 images of numbers, you get 2 images from MNIST, and the sum of the numbers in the image. You are supposed to learn to get 2 images and output the sum of the numbers in the images. Okay, it's not an easy task if you don't know anything. If you have just 2 images and the number, you have to understand what's going on. But maybe you know that this number is the sum of the numbers in the image. And what you can do with all these languages is to impose this knowledge, this understanding that there's an addition going on. In DPASP, you write this as two sentences. Basically, you're saying, well, the digits come from image, are coming from a neural net, and there's addition going on. Okay, and you can run DPASP, and actually you can run all systems that I mentioned with this problem. I'll just try to be very brief and summarize. So the orange line here is what you get if you learn a convolutional neural network without any understanding of the summation. If you don't know anything. So this neural network is trying to figure out things, and is learning is running slowly in terms of the number of epochs. All the other systems here, DPASP is the blue one, NeuroASP is the brown one, and dproblog is the green. All of them know that there's summation going on. They have this information, okay? But the difference is all of them are running for 5 epochs, okay? So this is what you get after 5 epochs. The difference you see here in the table is that DPASP is quite faster, okay? Because it was really designed to be as fast as possible for simple things. So it does 5 epochs over NNIST in 20 seconds. The other systems take minutes. And it is a bit unfair because this is a small problem. DeepASP is supposed to be very good. Whereas for large problems, probably DeepRoblog will be a lot better than DeepASP. So there is a trade-off here. But you can see that it does things really fast and a lot faster than the convolutional neural network. Okay, that runs 5 epochs in 29 seconds, and DeepASP is running in 20 seconds. So here's some information about DeepASP if you're interested. This is really work in progress. This is actually happening. We're being funded by local funding agents here, FAPESP, and by IBM. IBM has paid for Renato's work. It's been very nice work, in fact. And this is available. There's a tutorial. It's very simple, but you can probably get the feeling. If you feel free to contact us. If you want to help, please contact us. And there's a technical discussion at this recent AAAI workshop. Okay, so I will stop, and just say 2 things. That this combination of neural, probabilistic, logical languages are very powerful, very flexible. They can help us do a lot of stuff. There's quite a bit of understanding about their complexity, their expressivity, but there are many challenges when it comes to actually doing the algorithms and learning. So there's a lot to do, a lot to be done, and I think there's interesting work to be done. And thank you for the invitation. Thanks for the invitation. Thanks for the audience, and thanks for the sponsors, IBM and FAPESP and other funding agencies here. Thanks a lot.
Okay, Fabrizio, take it away.
Yes. Shall I go on directly?
Yeah, please.
Okay. So in my talk, I will briefly recap probabilistic logic programming and the distribution semantics with some examples. And then I will discuss the relationship to Bayesian network. And then I will talk about Markov logic network, which is a different way to combine probability and logic. Finally, I will briefly mention statistical statements, which are a logical way of representing statements about populations. So in probabilistic logic programming, the approach that gained most success is the distribution semantics. And it was named like that by Sato in his 95 paper. The idea is very simple. A probabilistic logic program defines a probability distribution over a normal logic program. So no logic program without probabilities, but possibly with negation. These programs are called instances of possible words or simply words. So you have a distribution over program. Then from the distribution over program, you build a joint distribution over words and interpretation and a set of ground atoms, or directly over queries, where a query is a ground atom, an atom without variables. And the probability of the query is obtained from this distribution. So the distribution semantics, as Fabio was saying, originated more than 30 years ago. Probably the first to speak about this type of combination of logic and probability was Dansin in the Russian conference on logic programming in '91. Then it was rediscovered many times and got its name from PRISM in '95. Here I will discuss 2 languages, which are logic program with annotated disjunction and Problog, which are the most recent and with the simplest syntax. These languages differ in the way they define the distribution of a logic programs. So this is an example of a logic program with annotated disjunction. So in these programs, the rules have a disjunction in the head, and each atom is annotated with a probability. So the probability of sneezing eggs is 0.7, and the probability of null is 0.3. This link that you find here is a link to a web application, CP-Lint, where you can try these programs online. So the first rule can be read in this way: if X has the flu, then X is sneezing with probability 0.7, and null, so nothing happens, with probability 0.3. I say nothing happens because I assume that null cannot be queried and does not appear in the body of any other rule. The second rule says that if X has a fever, then X is sneezing with probability 0.8 and nothing happens with probability 0.2. And then we have a fact, flu Bob and a fever Bob. These are certain information. They can be seen as disjunction where one of the atoms in the head is probability 1. So you have a distribution over the head of rules. How do you generate the non-probabilistic words, the programs that are the words? You do this by first grounding the program, substituting the variables with constant in all possible way, and then selecting one atom from each disjunctive head of each ground clause. In Problog, you have probabilistic facts. So, for example, using X with probability 0.7 is a fact, and when a fact is on ground, it stands for the set of probabilistic facts obtained by replacing the variable with constant. So this fact, flu sneezing X, can be seen as the fact that representing the fact that flu is an active cause of sneezing. So then besides probabilistic facts, you have rules, regular clauses. So the first clause states that if X has the flu and flu is an active cause of sneezing, then X is sneezing. Since flu sneezing X is probabilistic, then the conclusion of this rule is probabilistic as well. And the second rule is similar. So you have a distribution over facts. You obtain words by adding all the certain rules to each word and adding or not adding each grounding of each probabilistic fact. So for it, you first generate the grounding of the probabilistic fact, and then you generate a word by selecting whether to include or not each fact. So the idea behind the distribution semantics is this one. You have a query Q which is an atom, which is without variables, and you want to compute its probability according to a probabilistic program. You can observe that if you consider the conditional probability of the query given a word, W, this is can be determined with certainty because the word is a non-probabilistic program, so the query is either true or false in the word, assuming that the word has a single stable model. So the probability of a query Q given a word is 1 if the query is true in the word and 0 otherwise. So the probability of a query can be obtained by considering the joint distribution of the query and the words and summing out the words. Then the joint probability of the query and the word is obtained by multiplying the conditional probability of the query given the word times the probability of the word and summing out the word. And then this means that since this conditional probability is either 1 or 0 and is 1 only for the words that entail the query, you sum the probability of the words where the query is true. And this is the probability of a query Q. Let's see the words. So for the LPAD program, we have two clauses with a single variable and a single constant. So generating the grounding yields two ground clauses with a disjunction in the end. So we have two alternatives for two clauses. 2 times 2 makes 4 words. The first word is obtained by selecting the first head for the first rule. The second word is obtained by selecting the second set, the second atom in the head of the first rule and the first atom in the head of the second rule, and so on. So you obtain 4 words. Notice that each choice made is associated with a probability, so you can assign a probability to each word. So, for example, in the program, Sneezing Bob in the first rule was associated with 0.7, and in the second rule with 0.8. So you can compute the probability of word 1 as 0.7 times 0.8, and so and the same for the other words. Then you have to find out in which words the query is true. Sneezing Bob is the query. Sneezing Bob is true in this word, in this word, in this word, but not in this word. So it is true in 3 words. I have to sum the probability of W1, W2, and W3, which makes 0.94. For Problog, each word contains the rules of the program and a selection of the facts, the probabilistic facts. Again, the grounding, we have a single constant, we have 2 probabilistic facts, we have therefore two choices, each with 2 alternatives. So we have a word where both facts are present, 2 words where only a single fact is present, and a word where no fact is present. And the probability again can be associated to each word, where the absence of a fact is evaluated as 1 minus the probability of the probabilistic facts. Again, if you want to see where Sneezing Bob is true, Sneezing Bob is true in the word where we have both probabilistic facts and in the word where we have a single one, but not in the word when we have none. So the probability of Sneezing Bob is the sum of the probabilities of this word, which is 0.94. In logic program with annotated disjunction, you can have more than 2 atoms in the head. In this case, you can see 2 atoms, but the probability of this atom do not sum to 1. Here we represent disjunction with the semicolon. And in this case, when the probability of atoms in the head does not sum up to 1, it is implicit that there is an extra atom with the remaining probability mass. This extra atom, by convention, is called null, but the important thing is that it is not queried and it does not appear in the body of any other rule. So in this case, we have a program similar to the one before, but with a degree of sneezing. And by grounding the 2 rules, we get 2 ground rules, each with 3 alternatives in the end. So we have 3 times 3 words, 9 words. The query strong Sneezing Bob is true in 5, and its probability is 0.44. With Problog and LPADs, you can encode Bayesian networks, as already Fabio was saying. And for example, with LPADs, you can encode this network, the usual alarm example. You have to use a propositional atom for each equation variable, random variable equal to value. So for example, for burglary that has the value true and false, we have the atoms burg T and burg F. And then you have a rule for each row of the conditional probability tables. So for the variables without parents, we have a single rule. So for burglary, we have burglary with probability 0.1 true and burglary false with probability 0.9. Similarly for earthquake, for alarm that has burglary and earthquake as parents, we have a rule for each row of the table, and in the body we have the values of the parents. So, for example, if burglary is true and earthquake is true, alarm is true with probability 0.1 and 0 otherwise. So we have a certain rule. We can omit the second atom because we will have probability 0. So alarm true if burglary true and earthquake true. The second rule, second row, burglary true, earthquake false, alarm is true with probability 0.8, false with probability 0.2. And so the rule is alarm T with probability 0.8 or alarm false with probability 0.2 if burglary is true and earthquake is false. The interesting thing is that all the languages under the distribution semantics have the same expressive power, in the sense that there are transformations that can convert each one in the other. And in fact, nowadays they are mostly indistinguishable, for example, because also Problog has annotated disjunction. So ELPAD and Problog are basically the same. An example of a translation from an ELPAD to Problog is the example I showed you before, because these two examples, this logic program with annotated disjunction and this Problog program, are equivalent, define the same distribution. So this is an example of how to translate a logic program with annotated disjunction in Problog. A Problog program is already a valid ELPAD because probabilistic facts are annotated disjunction with two alternatives. You can convert probabilistic logic program to Bayesian network. How do you do it? For each ground atom A, you have a binary variable, a binary random variable A. And for each closed CI, which is disjunctive, you have a variable CHI that has all the atoms in the literals of the body as parents, and the values are the atoms, the name of the atoms in the head plus null. So, the conditional probability table for this CHI, which stands for choice variable, is this one. So the possible variable CHI equal to H1, H2, Hn, and null. And for the case where the body is true, so all the B literals which are positive take value 1, and the C literal which are negative take value 0. The distribution over the CHI variable is the one indicated in the head. For all the other values of the body, all the probability mass is assigned to the CHI equal to null value. This is because the rules has to have an effect on the rest of the program only if the body is true. If the body is false, the rule takes value null, which has no effect. Now we have to define the conditional probability table of the random variable associated to atom. So for an atom A, its parents are all the variables CHI of closed CAI that have A in the head. And the conditional probability table is a deterministic probability table, which has A equal to 1 if at least one parent is equal to A, and 0 with probability 1 and 0 for the remaining columns. So for example, this program is translated into this Bayesian network where the xi variables are the variable associated to atom, and chi ch1, ch2, and so on are the variable associated to clauses. So you can translate Bayesian network to and from probabilistic logic program under the distribution semantics. You can also deal with probabilistic logic by using undirected graphical models such as Markov network. So you have this network where that models a university domain where a student can be intelligent or not, can get good marks or not, depending on the course difficulty and the ability of the teacher. Each click of the graph is associated with a positive potential, and the potential associate a tuple of values of the variables in its domain to a positive real value. In this case, the probability of a word, so of an assignment to all the variables, is given by the product of the value of the potential applied to their domains, divided by that, which is a normalization constant that serves to ensure that the probability distribution sums to 1. You can also use a log linear model if the potential are all strictly positive. No potential is equal to 0. So you can represent the joint distribution as the exponential of a sum of a real weight W1, which can be positive or negative, times a feature, which is usually a 0-1 function. That, for example, can be, for the example before, can be expressed as 1 if not intelligence or good marks, and 0 otherwise. And the weight in this case is 1.5. A Markov logic network is a set of pairs where F is a formula in first-order logic and W is a real number. And they define a Markov network when given a set of constants. And the Markov network has one node for each grounding of each predicate in the MLN and one feature for each grounding of each formula F in the MLN with the corresponding weight W. So, for example, this MLN, for all x, if x is intelligent, then x gets good mark, and for all xy, if x is friend with y, then intelligent x, if and only if intelligent y. So friends have similar intelligence. Given constant Anne and Bob gives rise to this Markov network where you have one node for each grounding of each predicate. And
Fabrizio, just a reminder, we have 5 minutes left.
Yeah. And the probability of an interpretation, which is an assignment of truth value to all ground atoms, in this case is given by a log linear model where you sum the product of the weight associated to each formula I times NIXI, which is the number of true groundings of formula Fi in X. When you generate the Markov net, in practice, you use typing to reduce the size of the ground Markov net. So now I want to speak about an interesting and different problem. Fabio has shown you probabilistic answer set programming, where you have disjunctive rules, and you can also have constraints or rules without a head, which are used to eliminate stable model. And a constraint is satisfied only if some literals in the body is false. And you can have aggregates that Fabio has shown you. For example, usually aggregates appear together with a comparison operator and a guard, which is a variable or a constant. And for example, you can have this program where you have 4 birds, and each bird can fly or not fly. And then you have a constraint which states that the first aggregate counts the number of eggs such that fly X and bird X is 2, so the number of flying birds. and assigns it to the variable fb. The second aggregates counts the number of bird x and assigns it to b. And then it imposes the fact that 10 times fb is smaller than 6 times b, which means that the number of flying bird is smaller than 6 over 10 times b, so 60% of the birds. Now, since this is a constraint, it is a denial, this constraint imposes that actually the number of flying birds is greater than 60% of the bird. This program with 5 birds would have 2 to the 4, so 16 stable model without a constraint. The constraint cuts down the number of stable models or answer sets to 5. With this language, it is possible to express statements such as the probability that a random person smokes 20% or 60% of birds fly. While with the distribution semantics, you can only express degrees of belief or type 2 statements. So John smokes with probability 30%, John sneezes with probability 10%, tomorrow is going to rain with probability 10%, and so on. We have presented an approach for expressing probabilistic type 1 statement of this form CA pi L pi U, which means that the fraction of A's that are also C's is between pi L and pi U, where pi L and pi U can also be 0 and 1. And the semantic is that the words, the models of a word with the constraint pi L smaller or equal than the fraction of x, such that C of x and A of x is true, over the number of x where A of x is 2 is between pi L and pi U. So this language cuts the word where this constraint is false and permits to us to express statements such as 60%. Statements such as this one states that there are 4 birds with probability 0.4 each, and the number of flying birds is between 60% of the bird. So to conclude, I just briefly recap probabilistic algebra programming and the distribution semantics, shown that there is a relationship to Bayesian network, and then illustrated another way to combine logic and probability, which is Markov logic network. I've shown you a way to use probabilistic answer set programming to express statistical statement, and there are many directions for future work. One, for example, is how to perform inference from PSP and pasta without generating all the words. And you can have a look at the second edition of my book for details of the topics of this talk. Thanks.
Thank you, Fabio and Fabrizio.
Thank you, guys. All right, that was great. So we had a question. Again, please put questions in the Q&A rather than the chat. But someone asked about DPASP, about the software and open source. That was answered in the chat. So if you had that question, check there. Yes, it is open source and available. Other question, general question, appreciate any pointers. Given a goal, can facts be learned from a set of KRRs the same way a CNN, convolutional neural network, learns filters that optimize with regards to the loss function?
Well, I think Fabio can answer as well, but the answer is yes. There are many systems that optimize the probability of probabilistic facts and according to a loss function. And there are also systems that add the probabilistic facts when needed or probabilistic rules. So an example is DPASP of Fabio, and also for example, prob foil by the level group or sleep cover by my group. So there are many systems that can learn and that usually use either gradient descent or expectation maximization.
Yeah, that's it. Well answered.
And this area is, sometimes called it ILP, inductive logic programming, rule induction, which you can do in, both logics with and without uncertainty. So another question: for all these probabilistic logics that use disjunctive heads in the rules or which are based on ASP, there seems to be a conflict with what Benjamin Grossoff was saying, i.e. this takes us over the cliff of high complexity and thus would not be practical for realistic problems.
Oh yeah, there's a trade-off. Yeah, sure. We have a pretty clear understanding of the complexity of these things. If you add disjunction heads, basically it's like adding an NP oracle at some level in complexity. So you can feel that it gets harder. But the thing is, the programs get a lot more expressive and they get a lot shorter as well. So for example, if let's take a simple example. Suppose you want to code tree coloring in graphs. The program gets a little difficult to read and a bit long if you don't have disjunction heads, but it's super short if you have disjunction heads. So there's a trade-off. Basically, I guess having them in the language is useful, but you should not use them unless it's really useful, because it's a lot more complicated.
Okay, I'll ask one, maybe on behalf of a ghost audience member. So, Fabrizio, you showed, sort of the equivalence between in expressiveness between a few different frameworks. But then what would you, but we know there are trade-offs. This whole theme of the whole, at least KRR part of our day is about trade-offs. So what would you say are the, how you would choose them between them?
Well, the choice between a probabilistic logic and graphical model, I think should lean towards the probabilistic model when you're dealing with relational data, because usually inference algorithms for probabilistic logic generate ground the program only on the parts that are needed, while in a graphical model you need to generate the whole model to apply an inference algorithm on it. So that's the difference between graphical models and plain graphical models, and so the theoretical power is the same, but in practice the inference algorithms are for probabilistic logic are tailored towards the case where you have relational data.
Okay, great. So we're at time. So thank you again, guys. That was great. And now we'll take a little lunch break. We'll let